Chapter 18, as much as we need of it right now, is pretty well told using two ideas that we are already familiar with back from Physics 201. Before we get into those ideas, those sort of analogies, we have a definition to make. Suppose we have a conductor and we set up an electric field within the conductor from, let's say it's a long, thin geometry, and we set up an electric field this way. Positive charges, Q, that exist all the way along the conductor would be pushed to the right by the electric field. Negative charges, QE, electrons, and I think we maybe should think about electrons because those are the free particles in a metallic substance, in a conductor. So we have these loose electrons that if we apply an electric field are, in this drawing, going to be pulled to the left. So the charges move. And you can think of the moving charges like water molecules flowing in a pipe. Some pressure at one end, a different pressure at the other end. If there's a pressure difference, the fluid will flow. And we can talk about the speed of that flow, and we can talk about the speed from left to right of the individual molecules of that flowing fluid. And that's kind of where, that's the first sort of analogy even that I'd like to make. Flow. If we're here with a little, in a little entry counter, right? Every time a charge passes this point, click, I see another one goes by, click, click. Every time a charge goes by, we count it. The rate at which charge passes this point how much charge goes by in how much time? I'd like to define that as current, or specifically electric current. The symbol that I'd like to use, it's unfortunate, but it is what it is the letter I, capital I. You will sometimes see me use a lowercase I on the board. The textbook almost always uses a capital I. This is equal by definition. 3-line equal sign is defined to be current. Electric current is defined as the rate at which charge flows. This is the charge flow rate. Like when we talk about fluid mechanics, we talk about the mass flow rate, delta M over delta T. Or the volume flow rate, change in volume over change in time. So this is a similar flow rate, but now we're talking about charge flowing instead of mass or volume. What are the units of this thing? Well, charge has the unit of Coulomb. Time has the unit of second. So it has the unit of coulombs per second, which we define as amperes, or amps for short. One amp is 1 coulomb per second. How much charge is flowing by? Well, I watched for a second and I saw a coulomb of charge go by, so I have observed a current of 1 amp. Great. Okay, so what else do we need to say? Let's keep that idea in our minds. And at this point, we've been talking about fluid flow as a way to kind of think about what's going on, is that these electrons are like fluid molecules flowing through a viscous medium. There's some viscosity because as we'll see in section 18-8, which I'm actually going to leave for you all to look over, the electrons collide a lot of the time with the atoms that exist and that are kind of hanging out. The protonic, nuclei of the atoms that make up this conductor don't really move. They stay in the, metallic bond structure, the lattice structure that makes up the solid material. It's the electrons that can move around, and they run into the atoms a lot. And you could sort of think of that like a viscous fluid flow. The fluid itself has some resistance to its own flow in a way. But there's another analogy that I'd like to make, and not every 201 class covers this. But I know that if you took 201 with me, we did cover it. And I'm hoping that enough of us have seen this material before so that it's at least sort of familiar. I'm going to try to do my best to justify it. And if you are, if you're curious about it, let me know. We can talk about it. Suppose we have a length of, I don't know, copper. And this side we keep at a constant temperature of 100 degrees Celsius. And this side we keep at a constant temperature of 0 degrees Celsius. And the way we do that is by keeping this in a vat of boiling water and keeping this side in a bucket of ice. If this side is in thermal equilibrium with its boiling water, then it will be, the very end will be at 100 degrees Celsius. And if this side is in thermal equilibrium with the bucket of ice, it will stay at 0 degrees. And we keep adding more ice to make sure that this is 0. And we keep adding more water and more heat to make sure that this is still boiling. What happens is that thermal energy will flow along the copper. That this is conduction. This is how we get thermal energy from one thing to another, by directly linking them physically. And we can conduct thermal energy along the copper. Okay. How much heat is done per time? What is the rate at which heat is accomplished. The language is weird. I'm not transferring heat, I'm transferring energy. And the process I'm using to do that is heating. It's sort of like I'm not, when I push on an object, I'm not transferring work, I'm doing work to transfer energy. And this is the same sort of deal. I'm not transferring heat, I'm transferring thermal energy. And the way that I'm doing that is by doing heat, by heating. It's a verb, not a noun. I don't just have a pile of heat over here. I have energy, and if I want to move it around, I have to use the process of heating to do that. Okay, so how much energy is transferred through heat divided by time? And we call that, well, it's the rate at which heating is done. You can, if, so we can think of it like a thermal energy flow rate, right? Not a heat flow rate, but a thermal energy flow rate. We do call it heat current, which is a little bit confusing. We should call it thermal energy current, if you're asking me. But we do say that those are, we call it heat current, heat per time. Electric current, electric charge per time. And they start to feel pretty similar. If you check out, I think it's chapter 14 in our textbook, there's a formula given for heat current in terms of the properties of the material. Think of the conduction from the hot side to the cold side. The word conduction and conductor makes me think of a train, right? Like an old school train with a conductor, someone who comes around and like checks your ticket and makes sure that you're going where you need to go and whatever. If we're gonna think about this as a train, what do we need to know? We need to know how many people can fit on the train. How many rows of seats do you have? Which is like the cross-sectional area of that copper. How many lanes on the highway, in other words? We need to know how far we need to move the stuff from one end to the other. I'm going to call it L. We need to know how much, what's the difference, right? If we make this 1,000 degrees Celsius, that's so much more. The difference between 1,000 and 0 is so much more than the difference between 100 and 0. Well, yeah, okay. But the bigger the difference, the faster, the more it's going to flow. It's like, well, go back to the fluid flowing in the pipe. The more pressure we exert on one end, the faster the fluid's going to go. We need to know the difference between the high and the low. But changing one and the other, right? If we, instead of 100 and 0, we make it, you know, I don't know, 200 and 100. Well, that's really the same story. We've still got a difference of 100. From one side to the other, there's a difference of 100. And the last piece of the puzzle, the last thing we need to know, how good is this material at conducting heat? So this constant K is the thermal conductivity of the copper. If we know the difference in temperatures, the cross-sectional area, the length, and the thermal conductivity, then I can tell you how much current there will be. The thermal current that we're talking about here is communicated by particles. We change the kinetic energy of the particles as we move thermal energy through. The particles whose kinetic energy we can most change are the electrons. I mean, this all makes me think that this is a really good model for this. That somehow or other, I've got to talk about the pipe that I'm trying to get charge to flow in. And I need to know how well it flows in this particular pipe. I need to know how big a pipe it is and how far I'm trying to get that charge to go. And I need to know how strongly I'm encouraging it to flow. The greater the temperature difference, the more the thermal energy wants to propagate. The greater the pressure difference from one side to the other, the faster the flow. There's another equation that occurs to me here that describes flow of a viscous fluid, and it's a I never can correctly pronounce this person's name. I don't even know if I can spell it. It's something like that, which I'm going to pronounce Poiseuille, French. Well, no, like the person was actually French. Poiseuille's equation is most often talked about in terms of, it's viscous flow in small tubes, which has direct applications to blood flow in blood vessels. And the volume flow rate is, let me see if I remember. Divided by 8, something like that. This N with a kind of a trunk is eta, and it's the viscosity of the fluid. It's in the denominator because the more viscous the thing is, the less, like the more it resists its own flow. So the greater that is, the less the volume flow rate because the fluid is resisting its own flow. The length is still here. And I think I'm missing a factor of pi. Hold on a second. Let me look this up. It's just right here. It's in chapter 10 of our textbook, in case you are curious. I'm going to read more about it. Yep, I'm missing a factor of pi. Good. I like that. Because pi r squared is the cross-sectional area of a blood vessel. So there's an extra factor of r squared here, which I think has to do with the 8 and the eta, but you can kind of see the difference in temperatures and the difference in pressures. And it's the difference in pressure, the greater the difference is, the more we can push fluid through this viscous kind of self-resistance. This one I want to talk about, but it's the same sort of deal. The greater the difference, the more we can push through. All right. So here's what I'm thinking. The area, the cross-sectional area of this substance, this conductor that we're moving electrons in, it's still the cross-sectional area. The length that we need to move it through, it's still the length. And instead of thermal conductivity, I'd like to talk about the electrical conductivity. How good is it at moving charge? That's confusing. It's the symbol we turn out to use, but we've already seen sigma, and it was charge density. So I don't want to. I'm just going to call it. Well, I'm just going to call it K for now. Electrical conductivity. And the missing piece. If I want a fluid to flow, I need a pressure difference. But there's another way I can get a fluid to flow. And that's by making a height difference. If the pipe has some descent to it, fluid's going to flow down because gravity. Because gravity. And the greater the difference in height, the more energy the fluid is going to have when it reaches the bottom, the faster it's going to be going. The greater the difference in the gravitational potential energy at the top and the bottom, the bigger that difference is, the more kinetic energy we can have at the bottom relative to the top. The more we can speed up relative to how fast we were going at the top. The greater the potential energy difference, the greater the kinetic energy difference. Assuming everything else stays the same. Interesting. The greater the potential energy difference. and I start to think about charge. And I start to think about differences in potential energy from one place to another. But as soon as I start thinking about charge and potential energy, I start thinking about electric potential. It's not about the charges themselves, right? Like, it's not about the fluid itself flowing in the pipe. It's about how different is the top and the bottom. GH. What planet are we on? And what's the height difference? So I don't really want to talk about the potential energy itself. I want to, I, hmm, it's the electrical environment as opposed to the gravitational environment. The, the greater the difference in the electrical environment from the top to the bottom, from the top to the bottom, I don't know, the greater the difference, anyway, from one end to the other of this conductor in electric potential, the more the charges will flow. Here's what I'm thinking. Just by analogy with that. What do you think? See, I think it makes a certain intuitive sense. How good is it at moving charge? How many lanes are there on the charge highway? How long is the road? And how much gas do we start with in the tank? To what degree is one side different than the other? How much of a electric potential downhill are we experiencing? Let's see if this corresponds to anything useful. Now, the difference in the voltages, that I could write that as delta V, the potential difference. Delta V. And now your work Thursday with the Ohm's Law lab. For a given material, for a given geometry, for a given material, let's say it's copper, and it has a cross-sectional area this much and a given length. Take that piece and use it over and over again in the same experiment. This expression is constant. This constant, K, is a function of which material we're using, and as long as we're still using copper, it doesn't change. And as long as we're still using this particular piece, the area and length don't change. So this configuration, if true, right, I'm still not sure, it's got a question mark. we multiply, I'm just thinking, we multiply by L, divide by K, and A, divide by I. So these L, K, and A are those constant things. So this left-hand side is constant. That the ratio between the voltage, the potential difference from one end to the other, and the current flowing through that much stuff is constant according to these parameters. That if you graphed potential difference versus current, that y over x, that slope would be constant. And in your work in the Ohm's Law lab, you know what that should be. I mean, this obeys Ohm's Law really well. If L, K, A is equal to resistance. If you look up resistance in chapter 18, you won't see a formula that looks like this. It'll look slightly different. And that's because our formula is built for electrical conductivity. The section in the textbook that deals with this talks about not the conductivity, but the resistivity. It's the anti-conductivity. It's the reciprocal. So they define 1 over what I'm calling K as resistivity. And it's a property of the material, right? Anytime you've got copper, we can look up its resistivity somewhere in a table. So if division by K is rho, now we've got a definition for the resistance of some conductor, some electrical element. What is its resistivity? How long is it? Divided by the cross-sectional area. I leveraged the fact that we already knew Ohm's law. V divided by I should be R. Well, at least according to Ohm's law. We know that this is a thing that obeys Ohm's law because the thing that is the thing that is doing the job of resistance in this equation, as far as holding it up next to Ohm's law, that this thing is constant. If this thing were some function of some other variable and could change, well, this is not an Ohm's law obeyant material because its resistance could change. What's ohmic about it is that the resistance is constant for a given geometry and a given material. The resistance is what it is. That the ratio between voltage and current will always be R. Cool. We're actually almost done with the material I want to cover from chapter 18. There's one more definition I'd like to make. And it's actually really straightforward. Power. Power is something we defined back in Physics 201, and it's the rate at which energy is transferred. We wrote it as work done divided by time. Now, the work done moving some charge through a potential difference but charge moved per time, you just defined that. That's current. So the power transferred by pushing charge this fast through a potential difference is just the product. This is true all the time for any kind of electric device. If it's a resistor, some sort of thing that obeys Ohm's law, then we can make some modifications here. We could replace I, for example, with the potential difference across the resistor divided by the resistance. And we could make that replacement here for I delta V over R. But that's delta V times delta V. Okay, sure. If instead of I, we could replace delta V with IR. Right. That's the story. This definition is true all the time. These two definitions are true for ohmic materials, ohmic electric devices. That is as much of chapter 18 as I'd like to cover right now. Sections 6 and 7 we will come back to, and I'll cover them later. Sections 8, 9, and 10 I'm going to leave for you to go through. It's possible that there is a mastering physics question about them, but it should be relatively straightforward based on the examples that are worked in those sections. And that's the story. Next segment.